The purpose of this applet is to demonstrate the idea of the confidence interval. Now, a confidence interval is what we use to estimate a population parameter. In this applet, we are going to estimate a population mean, represented by mu, knowing that the population's distribution is normally distributed. The green line here represents the mean line, the central line. And the way this applet is set up is that we are going to generate many confidence intervals, and we are hoping that these intervals will intersect this green line here so that it may provide us with an estimate as to the population average. Now, what we will do first is we will demonstrate how the confidence level affects a confidence interval. So I will choose a single sample at 99% confidence. Now, this sample here that's being displayed has a red dot. This red dot represents the sample average. These black lines extending from the red dot represent the margin of error. Now, the margin of error is what we use to obtain our estimates. We know the sample average will not be exactly equal to the population average every single time. So we generate what's called a margin of error to give us an interval so that we may obtain an estimate. And if our interval intersects this green line here, then we tally it as a hit, and we go ahead and compute the percentage of those intervals that hit, and we have an idea about what our population average is. So with this particular example, we see that our interval stretched out, and it did intersect the mean line here, so it was counted as a hit. If I shrink the confidence level down to 95, notice that my margin of error shrinks with it. And this is because the margin of error is directly proportional to the confidence level. So if the confidence level shrinks, the margin of error will shrink with it. And we can see that as I change the confidence level down from 99 to 80%, we have much less of a margin of error. Now, a margin of error is not saying that we are more or less accurate in this case. The margin of error is what allows us to test values inside of the interval. So this is not a good thing. If you lower your confidence, you may shrink the margin of error, but you're also saying that there are less numbers to choose from as an estimate because you're less confident that the sample average is close to the population average. And if you increase the confidence level, then you increase the margin of error, and graphically that means that you stretch out these black lines to encompass more possibilities. Now, if I choose a second sample at 99%, we see that we generate a second confidence interval. The red dot on the second line there represents that sample mean, and the black lines again represent the margin of error for that particular interval. Now, in classroom settings, you typically compute just one confidence interval, but in real-life settings, you often compute many confidence intervals based on many samples. So we'll go ahead and compute that, generating sample after sample. And right now we have a good percentage of my samples hitting this mean line at 99%. And right now we've generated 30. I'll continue to generate. Okay, so from my first 50 samples that I've generated, every single one of those confidence intervals intersected the mean line. Now, the idea of the confidence level is that this percent that represents the confidence level should be reflected in the percent hit if I were to generate many samples. So right now I've generated 50. If I generate another 50 On top of this, we see that we have two intervals that did not intersect this line. So after 100 samples, my percent hit is 98. My confidence level is 99, and these are relatively close. And this is the idea of the confidence interval, is that when you generate many samples, the percentage of those intervals that hit a estimate should be reflected in the confidence level itself.